Here we have the heights, h of n, in meters of a golf ball thrown by an astronaut vertically upwards from the surface of the moon n seconds after it was thrown, are as follows. So we're given what would be time 0, and then we have 1, 2, 3, and 4. So let's write these out. 1, 16.2, 29.8, 41.8, and 52.2. Let's write down our differences. So it's going up 15.2, then it's going up 13.6, then it's going up 12 exactly, and 42 will be 12.2, 10.4, sorry, 10.4. Second differences are going down, minus 1.6, and they're all the same here, so we can say that this sequence is quadratic. Same second difference. Therefore quadratic. Let's work out A, B, and C of this quadratic sequence. Center it a little bit. Question 1 is, what height is the ball thrown from? Well, that's h0. It's thrown from 1 meter above the ground, which you can all see. So let's look at the A, B, and C. We have it, well, we have C. C is equal to R1. 2A is equal to minus 1.6. So A is equal to minus 0.8. And as you all know, because you've practiced so many, A plus B plus C is equal to term 1. Just be careful that we take the 1, not the 0. That's 16.2. So C is 1, A is minus 0.8. So 1 minus 0.8 plus B is equal to 16.2. So that would leave B being 16. So our term Tn is going to be minus 0.8 n squared, or t squared. B is 16 plus 16n, and plus C, which is plus 1. So we've shown it's quadratic. We found A, B, and C. Use calculus to find the max height. So we have Tn. So this is the height. Let's call it, we'll change it to T here because we're dealing in seconds. 0.8 t squared plus 16t plus 1 is the height after t seconds. So dh dt, we differentiate. Dh dt is going to be minus 1.6 t plus 16. We let these equal 0 to get the max height. So we're going to get 1.6 t is equal to 16. So the max height will occur after 10 seconds. So let's find t10. It's going to be minus 0.8 by 10 squared, put in 100 if you know it, plus 16 by 10, 160, and a 1, so 161. So that's going to be minus 80 plus 161, which is equal to 81 meters for the max height. And then the second part was about acceleration. Now I'll just write out displacement. They're asking you to look at displacement. Ut plus a half at squared is my displacement. ds dt will give me u plus twice a half, which is 1, u plus at, which you all know is speed. And if we differentiate this twice, d2s dt2 will give us a. So we just need to differentiate r1 twice. So we've got the h dt here. So if we differentiate it twice, d2h dt2 is going to be minus 1.6, which is acceleration. So ms to the minus 2 is what acceleration is here. Question 10, we're given velocity in meters per second of a car. We're given time 0, 7, 8.2, 9.4, 10.6. These are all going up the same amount. This must be linear. 11.8, and we are asked to show it's linear. So let's just get our first difference. Show it's the same. 1.2, 1.2, 1.2, and 1.2. Same first difference, therefore linear. And the initial velocity is t is equal to 0. When time is 0, we have our initial velocity of 7. meters per second. And what's happening here? Well, what's happening? The car is getting faster by 1.2 meters every second. So constant acceleration, A is equal to 1.2 ms to the minus 2. Straightforward enough for question 10. And then finally in this section we look at question 11. We're given the population of unicornia at various dates, 70, 80, 90, 2000, and 2010. And we're asked to write out the differences up to the third. So this must be cubic. So I'll just write 70, 80, 90, 2000, and 2010. We're asked to find 2020 and 1960, so just put them at each end. And 20. So 1.1, 1.3, 1.7, 2.9, and 5.5. Let's have a look at our differences. We're going to need to work our way back up. 0.2, 0.4, 1.2, and 3 with 2.5, 2.6. That's the first difference. Second difference, up 0.2, 0.8, and 1.4. You can see here the third difference is 0.6. So it's cubic. Same third difference. And if we work our way back up to get 2020, to keep the 0.6 down the bottom, I'd have to have a 2.0 here to get 0.6. And just look at the pattern. 1.2 plus 1.4 is 2.6. 2.6 plus 2.0 will be 4.6. Just highlight these are what we're adding. And then 5.5 plus 4.6 will be 10.1 in millions. And then working our way backwards, we'd also have a 0.6 here. 0.8 minus 0.6 is 0.2. 0.2 minus 0.6 is minus 0.4. The next line up, 0.4 minus 0.2 is 0.2. 0.2 minus 0.4 is 0.6. Working our way up, 1.3 minus 0.2 is 1.1. And 1.1 minus 0.6, population in 1960, 0.5 million.